So now we come to the integral of an area in polar coordinates. That is basically the integral of a radial function. The integral for area in polar coordinates. Here we define what a radial step is, function is, then radial step function for polar coordinates, and then we like how we add ordinate set for function. We have a radial set for a radial function. Then we use it for step function. We defined because function is akin, so you can use it the same way. And then you use the integration for a step function, and we move to a general area of a sector using an integration function of a radial function. So first we define basically the essence of a radial function to some extent. So let f be a non-negative function defined on interval. This is actually kind of important. Defined on an interval AB where 0 less than equal to b minus a less than equal to 5. And this is because so that later when you use step function, right, you find the area between two angles, theta k minus 1. It's less than 2 pi, so the area actually throughout the circle, if it's not more than 2 pi, it just be between that circle. But if it's greater than 2 pi, then it'll overlap and then you have to take the again. So that's why we just define it in such a way. Then the set of all points with polar coordinates, as we discussed before, are theta, that is phi n, the inequality zero less than equal to r less than equal to f of theta is called, it's basically the reason set satisfying the inequality is called radial set of f of the real function over AB. So we can just basically describe here we have one point here and make something like this. It's so let this be theta 2, this be theta 1, this be theta. So say this theta is equal to b greater, no? So theta 1 is b h. And then this theta. So from this interval, and then you can probably then you can just define step function like this, like this, like this, like this, yeah, to approximate the area. So then we say the radial set of a step function S between theta k minus 1 theta k, and there are n such intervals, so it contains from A to B, and S of theta k or S of theta k in that interval k to k minus 1 is equal to sk. Then we come and the radial set of theta is k as angle, well, the difference of that angle, right? For the sector, theta k minus theta k minus 1, because we take this k minus 1, it has the area, so we take that angle, and we define this area as half theta k minus theta k minus 1 is k square by definition of sector. And since B minus A, this is why you define no overlapping of areas. Then we add up all them. The whole set equals half of sigma k equals 1 to n s k square. That's from the theta k minus k minus 1. And since we know this is an input to c theta, where square of theta equals s theta square. The integration of the radial sets. Theorem 2.6. That is, let R denote a radial set of a non-negative function f over an interval ab, where b minus a is in between 0 and 2 pi, and assume that R is measurable, the radial set. If f square is integrable, you can prove f square is integrable by saying that since it's the radial set of a non-negative function, and so on and so forth. But if f square is integrable on ab, the area of R is given by a of R equals half of integration of a to b f square theta d theta. That is, let's just write it down. Basically, the area of the sector. So let's prove it. Say we choose two-step function as comma t such that for all theta in A, this holds. Then let capital S and capital T denote their set, radial set. Now, since S less than or equal to F less than or equal to T, then F less than or equal to A of R less than or equal to A of T. Now, S and T are radial step functions, and we proved in the previous episode just summation of the different step region. So we can just say A of x is equal to half of A to B square to B A theta, and A of t, and then this capital T there, that is equal to half A to B square of theta d theta. Now we multiply equal these by 2. So 2 A of S is equal to A of R is less than equal to 2 A of T. Now S square and T square are arbitrary step functions. Since so y is an arbitrary step function, you can say S square less than equal to so less than T. So since T square is non-negative, and S will be also non-negative. Then S square is non-negative. It is integrable basically, but we already say it is integrable, but it has lower integral, upper integral. So we prove that by that theorem, and also since S n equal to d theta. We also know S square is less than T square. So all this here, and then all this here, and also since it is integrable, S square is integrable is equal to I, the lower and upper bound. And also since it is only one value, it can be only satisfied by I. And since you only one function, arbitrary step function, you can make it really small. So the only thing that actually exists between them is just put this way. Yes. So then since this is 2 AR is equal to this, okay, that